Recording is rolling. It is Friday, October 25th. Gonna do an ellipse activity with you guys. You guys got some string and some scissors. We'll do that here pretty soon. You guys got your notebooks out. Have you guys draw something with that string in your notebooks? Do ellipse activity. Yesterday, I started talking about universal gravitation. So gonna pick up on that story. Have you guys do some calculations by the end of class. There might be a little bit of overlap between what I talked about yesterday and today. Each class I ended up by the bell yesterday, a little bit different spot. So a little bit of overlap. Maybe this is on the second time, which might not be bad either. Okay. Textbook puzzles. So I gave you guys some textbook puzzles a long time back. Here for my honors class, here I'm doing a video for honors and conceptual will be similar today. So my honors classes looks like this is chapter 6 and 7. For my conceptual class, it's chapter 8 and chapter 9. Right, so you've had that paper a while. We haven't really looked at it in some time, but let's have that due next Friday. I think it'll be a good due date because I want to solve some of those with you guys in class, give you guys some class time to work on those. So I think 1 week from now would be a good date for those. Next week, I'll get you guys your next take-home quiz, which is going to be on the same content as the homework puzzles and the ones we've been doing in class for a while. Today is picture retake day. If you need your picture taken, just go to the gym at some point today. Right, so let you guys figure that out. I have an update on hurricane makeup. So of course we missed a few days because of the hurricane. So what I'm getting is in spring, there are a couple of days in the spring that were holidays that are now going to be school days. And also to make up some more time, in November, there are going to be no early release days. So Fridays are just going to be regularly. So we'll have regular schedule Friday, all November, and also 1 day in December. Okay. So you guys got all that? Okay. One more thing. Next week is going to be a Say No to Drugs Red Ribbon Spirit Week. So here, I'll tape this up in my room, but real fast. Monday, too classy for drugs. Wear white, wear pink, wear blue, wear purple. Tuesday, future, too bright for drugs. Wear Dion. Wednesday, team up against drugs. Wear a jersey. Thursday, scare away drugs. Wear a Halloween outfit. No mask. Friday, say no to drugs. Wear red. Follow dress code. There you go. Got Red Ribbon Spirit Week. But you guys got on your desk, you guys got some string. You might possibly have a loop that's already tied. If you do, maybe you're a little bit ahead. Or maybe you have a length of string, possibly already cut some this morning. Or if not, you have a ball of string, so you can do it as I'm doing it with you guys. Cut something, let's call it about 20 to 30 centimeters. All right, bam, length of string right there. All right, then let's tie this into a loop. So cross one end over the other end, push it through, kind of like you're starting to tie your shoes. Okay? And then just do that one more time. So repeat that. And see, pull that. And now you have a nice knot. Look at that. I got a loop right there, a loop of string. All right, so everybody's got a loop of string, right? Loop of string. Okay. Now what I do is I'm going to do this with 3 pens. 3 pens. If you have 3 pencils, that would be really helpful for what we're about to do. If you don't, then well, try to make do with what you got. Okay, try to rig up something real fast. Now, 2 of these pens I'm going to put down. Let's say like right here and here. Right, I'll mark some points. You guys see a couple of points I just marked? A couple of points right there. Right. We're gonna keep these pens locked in place right on those points. Then take my 3rd pen and move it out here. Right. Ooh, guys, what shape is that? Triangle. Now, this 3rd point, I'm going to go all the way around. You guys go ahead and do the same thing. So I got the first 2 pens locked in place. And this 3rd pen, I'm going all the way around. A little better there. All right, that looks pretty good. Right there, right there. Okay. All right. You guys do the same thing in your notes. Right. And the shape you just drew, that has a name. Because what's that shape called? That's called starts with an E. Ellipse. Aha, ellipse. Let me jot that down. Ellipse. Right. And did you guys study ellipses maybe in algebra 2, possibly? Maybe? I did back in the day, but that was a long time ago. Right. Or maybe you know this anyway. I don't know. Because these 2 points right here, they have a name too. It starts with an F. Each one is called a. What do you think? Starts with an F. Focal point, maybe? Focal point? Or label it. Focal point and focal point. focal point. Right. Hey, what if those two focal points were exactly on top of each other? Maybe like this X right in the middle, and you did the same thing with the string. Would that be more like a compass? And what shape would that have made? A circle. I'm going to jot that term down here too. So circle, just so I can do a comparison between these two shapes. Now, what you actually drew is actually an ellipse. Hey, is a circle just a special kind of ellipse? Yeah, the circle is just a special kind of ellipse, isn't it? Right, where are we going with this? So what if I draw a line through these two focal points and also goes through the center? I'm going to dash off this line. Isn't that the longest line that I can draw across the ellipse? Go through the two focal points. Right. It looks like mine is 15 centimeters long. Right. So mine's 15 centimeters. Right. And then what if I go through the center, perpendicular to that, go across like the shortest way I could go across? This one looks about, I'll call it about 12 centimeters. Right. So it looks like 15 centimeters this way or 12 centimeters this way. Okay, guess that? Okay. And now what if I take half of each of those to get these arms? So I guess this would be 6 centimeters. I'll call that side A. So side A is 6 centimeters of mine. And the side B, I guess, would be 7.5 centimeters. Side B. Okay. So I got side A and side B. Okay. And what if I sort of square that off tight? Well, not actually a square. Right. Actually, guys, what shape did I just make right here? This is called a what? A rectangle. Aha, rectangle. And what is the area of that rectangle equal to? A times B. Right? Isn't that true? A times B would be the area of that rectangle. Right? Right. Now, let's make believe for a moment that this circle, this ellipse, what if I squashed it a little bit into a circle? Or if your two focal points were right on top of each other, that would also be a circle, a true circle. Instead of A and B, I could just call out the what of the circle? The radius. And this rectangle would be actually a what? A square. Okay? Okay. And again, assuming this is a circle, if it was a circle, right, how many of those squares would it take to fill up the entire circle? That square has some area, it'd be r times r, that would be r squared. How many of those do you need to fill up the entire circle? Pi. Aha. I'm gonna jot that down. The area of a circle is, I bet you guys knew that, right? Pi r squared. Yeah, you need 3.14 of those squares. Okay, now that's true for a circle. What do you think is the area of an ellipse equal to? I bet you can figure it out. Huh? I'm going to write a formula right here. What's the formula for the area of this? Because this is actually an ellipse, isn't it? Right. So maybe I could be referring to this. Right. You guys see this rectangle with the area AB? You guys see that? How many of those rectangles do you think it takes to exactly fill that ellipse? Take a guess. Do you think it takes more than 3? Less than 4? Pi. Aha. That's it. Pi AB. There you go. That's the area of that ellipse. Pi AB. Okay, you guys got that? Makes sense so far, right? All right. How about let's go back to a circle for a moment. All right. One perimeter of a circle has a special name. It's called circumference. So one trip around the circle, circumference, is equal to, what's the formula for circumference? In terms of its radius. Like whatever the radius is, so suppose it's like 1 meter. How long would it be all the way around? 2 pi of those, like 6.28 meters? I'll call this 2 pi r. Circumference equals 2 pi r. Okay? You guys get that? Okay. Last question on this page of notes. What then is the perimeter of an ellipse equal to? Like, okay, I see A, I see B. I wonder how long it would be to walk around here. Like, how much ink does that take to walk all the way around? Nobody knows. The most brilliant mathematicians in all of history have never been able to solve that. Nobody knows. Well, there's a fun mystery. All right, let me flip my screen over here. Oh, whoops. Trying to get used to the system. I hit the wrong button. Hang on. Actually, I didn't want to do that. Are we? Is that my computer screen? That was the same thing. I got to get I'm gonna pull up some video demos. I think we're okay. I want this one. This one right here. Okay. That's right. All right. I already got this zoom on pause. Let me just unpause this. Um, resume. All right, we're back. So I got an animation for you guys. Let's go back in time about 2,000 years ago. Yeah, there's a little crossover from yesterday. Maybe this would have fit better yesterday, maybe, but we'll do. So 2,000 years ago, and you ask somebody, what's the model of the solar system? Maybe they draw something like this, and here's an animated version. What did they put right at the center? Guys, what is that right at the center? The Earth, right? Now, hopefully you never did learn this because this is not accurate. This is not the actual model of the solar system. This is what people thought 1,000, 2,000 years ago. And here's the sun going around, and here's guys. Who is this and who is this? Mercury and Venus. They think now some versions of this maybe you can kind of figure out they orbit the sun. Maybe who's this guy right here? Is that the symbol for Mars? Right? You guys know that, right? Is the symbol for Venus is the symbol for female, and the symbol for Mars is the symbol for male. You guys know that? Right? Okay. Well, now you do. Now you know it. Right? Okay. So from the point of view of Earth, you look up in the sky. Look up in the sky. It looks like everything's just going around the Earth, right? Let's say you pay real close attention to Mars, guys. Look real close at Mars. Watch this. So Mars is going around counterclockwise. What the heck is that? Makes this little loop-de-loo in the sky. That's called a retrograde. So periodically, it's going to look like Mars actually switches direction and goes back kind of clockwise relative to Earth, and then continues back counterclockwise. Okay? Now, people had no reasonable explanation for why that would be. You can build it into the model. This is called a Ptolemaic model. Greek guy Ptolemy from thousands of years ago. Okay? But there was no explanation for why that would happen. You could say, well, I guess I could predict like into the future that'll happen periodically, sometime, but I don't know. You can see for other things too. Look at all these other loop-de-loos in the sky. Now the sun probably looks like it's going just regular circle. Same thing for the moon, but some of these have these retrogrades built in. Okay, and nobody could figure this out until along comes a guy named. Who was the guy who put the sun at the center? Copernicus. You guys see it just switch? It just switched. Okay, now we got the sun at the center. That's called heliocentric. Helio-sun, centric is the center. Heliocentric, put together, the sun-centered model. He says, hey, I think the Earth is just one of many planets that are actually all orbiting the sun. And then if you look at the observations of what we see in the sky, it all aligns perfectly, except that this is an even better model because it's a simpler model because you don't need all those retrograde movements that don't make any sense anyway. Like why would something just spiral in the sky randomly, right? Because it doesn't, because everything's actually orbiting the sun. Actually, if you want to be really strict about it, all objects in the solar system are actually orbiting what's called the Berry point, like the center of mass of the whole solar system, including the sun. Now, the sun is like 99% of the mass of the solar system, so you could basically say it's orbiting the sun, and that's what we're going to say. Right? But more specifically, yeah, there's some Berry center between things that are orbiting. Like between the Earth and the moon, I could say the moon orbits the Earth, but more strictly speaking, there's a Berry point, there's a Berry center that's inside the Earth, but it's kind of close to the surface. Right? Between Pluto and its big moon, Charon, their Berry center is actually outside of Pluto, so they kind of orbit a point that's outside of Pluto. Anyway, so that's how it works. Right? But yeah, solar system, we got this sun-centered model, this heliocentric model. So we got that. Okay. Let me find my PowerPoint slides. Right. So yesterday in class, I got to a little bit different points with different classes yesterday, and I know it was the end of class, so there might be a little bit of overlap. You might get a little bit of a review here. That's okay too. So after Copernicus, but before Newton, Kepler, a guy named Johannes Kepler, gets hold of this mountain of very precise astronomical data. And after pouring through this for years, is able to come up with the actual motion of planets. They're actually not circular orbits. They're, what shape is that? Ellipse. That's what you just drew in your notes, isn't it? That's an elliptical orbit. And the sun is actually at one focal point. That's also true from the Earth to the moon. The moon is orbiting the Earth, and well, you basically put the Earth at a focal point. So similar idea. Right? These orbits are pretty close to circles for planets, but a circle is not actually super stable because if it was going any slower, it would just spiral and fall into the sun. So an ellipse is a more stable orbit. Right? And some orbits actually are highly elliptical, like comets. Comets are highly elliptical orbits, right? There's a second law, equal areas at equal times. There's this third law. There's this, if you square the time to go around and cube the average distance, right? That proportion is the same for all objects orbiting the same star, in this case, the sun, right? So if you take the ratio, t squared over r cubed for Mercury, Venus, and Earth, and Mars, and Jupiter, like any planet in our solar system, it's the same ratio because we're all orbiting the same sun. Okay? If you want to make that an equation, like on the right, this is an updated version. You have to bring in Newton, which we're going to do here in a minute. Right? So Newton was the first guy in history to, well, do a bunch of things, including explain why the orbits are elliptical. He says the only math that would describe an elliptical orbit is this relationship right here. There's an inverse square relationship between the gravitational force and the distance between any two masses. Right? And he knew there was a gravitational force. He was also the first person to make the connection that the moon orbiting the Earth and an apple falling straight down from a tree is the exact same phenomenon. Right? Only the moon doesn't fall down from the sky because it's moving so fast to the side. That's really the only difference. It's moving so fast it has a tangential velocity. Figure that out. Okay. Now, why 1 over the distance squared? Go to this inverse square law. Did we talk about this yesterday? I think we did. Here, so quick recap. Look at a candle flame. Wow, that's really bright. You back up twice as far away. That light cone covers 4 times the area. Therefore, your eye, which is a fixed size, captures 1/4 of the light. Back up 3 times far away. Now that light cone covers 9 times the area because you have to think in 3D, right? 3 times as high, but also 3 times deep into the page. Therefore, your fixed eye size only captures 1/9 of the light. Light works like that. Electricity works like that. Gravity works like that too. So living in a 3D universe, it's a consequence of that. Right? Right. Then I think I also took to round this out, make this an exact equation. So this force, guys, which force is bigger? The Earth pulling the moon or the moon pulling the Earth? The same. Yeah, there's Newton's third law. So this force is the same both ways. This force is proportional to each mass of the Earth, mass of the moon, inversely proportional to the distance squared. Guys, what distance is that? Is that a surface to surface or a center to center distance? What is that? Center to center, right? And if you want to make that an exact equation, you have to bring in this capital G, this universal gravity constant, both as a number and also some units to turn kilograms and meters into somehow newtons, right? And this G will round this out. I told you guys Von Jolly figured this out. He puts up this scale. He has it all balanced. Mass on the left, mass on the right. It's all balanced. It's all good. Then he rolls big old 6 tons of lead underneath the left mass. He knows the center to center distance. And this whole scale turns a little bit counterclockwise. Then he takes a restoring force. I put like a red apple here to represent the restoring force. And the whole scale turns back and evens out again. Right. Now, Von Jolly knows Newton's law of gravitation. He's just trying to chase down what is that constant. So he takes this restoring force, divides by this mass and this mass and this distance squared, boom, right there. It comes up with this G, and you can change out the masses and this distance, and it doesn't matter. You always get the same universal gravity constant. Okay, so that's how we know that. Now we can make an exact equation out of this. All right, so here, since we have a few extra minutes in this class, I'll kind of go over this with you guys. This page I mostly made for my AP students, but I want you guys to at least see how this works. Okay? So what if you're comparing different planets? You guys think different planets have different gravity fields, maybe? All right, so let's check this out. What if there's a planet somewhere out in space that has let's call it 3 times the radius of Earth and 7 times the mass. I'm just making something up. Right? Now, pause for a moment here. If it was 3 times the radius, that would be 3 times the diameter also, wouldn't it? 3 times the diameter, 3 times the radius. Right? If you knew nothing else and you assumed it was the same density, I'm saying, so for instance, right, how many times the mass should it be? You guys remember a poster from a long time ago called Scaling? You guys remember scaling? Guys, if you're 3 times the width and 3 times the depth and 3 times the height, what is 3 times 3 times 3? Is that 27? Right? So if it was the same density as Earth, it should be 27 times the volume and also 27 times the weight, or 27 times the mass, I should say. 27 times the mass, right? But I didn't say that for this planet. I made up a mass. I said, it's supposed to be only 7 times the mass. Guys, if it's only 7 times the mass, that's not very dense, is it? Let's look at 2 aspects. We're looking at density here in this gold box and gravity field in this green box, right? So let's start with density. So density is mass compared to volume. That's this right here. See, density of Earth is the mass of Earth compared to the volume of Earth. Volume of a sphere is 4/3 pi r cubed. Now, you can still get the ratio of the densities correct, even if you don't know the exact volume of a sphere is 4/3 pi r cubed, if you don't know the 4/3 pi bit, because that cancels out. Right? The important part is the scaling part. You have to get the r cubed. Right? Anyway, if you plug in the ratios, I got 7 times the mass and 3 times the radius, you can come up with this density. And look at that, 7/27. That's what, approximately 1/4. So notice this is a very small mass planet. This is very small density. So maybe it's like made out of styrofoam or something, right? Well, let's look at gravity field. Now, gravity field, I'm going to rewind a little bit. I should make a specific poster for this. I probably will in the future. Okay? Guys, how do you go from force to acceleration? You divide by what? Newton's second law of motion. What does Newton's second law of motion say? F equals ma. F equals ma. So if you want to go from force to acceleration, the connection is the mass of the object. Do you guys remember that Galileo experiment? Galileo dropped a bunch of stuff off the Leaning Tower of Pisa and all fell at the same rate. Light stuff, heavy stuff, it all hit the ground at the same time. It was all accelerating the same. So what I'm trying to get at is go back to this formula here. Now this formula is a force formula. How can you get the gravity field from this formula? All you have to do is eliminate which variable? This mass right here, right? Let's explore this one a little bit. I want to make sure you guys get this. Let's do a specific application. Let's go to the surface of the planet, because this is going to help us figure out gravity field anyway. Right? Guys, could that force represent your weight? Like your weight's a type of force, right? You step on a scale, there's some downward force that's your weight, right? You guys get that? Right. Suppose you ran some numbers. Okay, suppose you ran some numbers. You want to figure out what is my weight. So capital G is right here, so you can plug that into your calculator. We'll do some calculations later in class today. So you plug that in. This capital M could be the mass of the Earth. So I'm going to give you guys that number later today. You plug that in. Right? Lowercase m, that could be what mass? That could be your mass. Maybe you're 50, 60, 70 kilograms, probably somewhere in there. So you plug that in. And here, guys, critical thinking question right here. Critical thinking. What would you plug in for this R? What is the distance between you and the Earth? And don't say 0. Because if you follow this formula, what's the distance between your center of mass here at the surface of the Earth and the center of mass of the Earth? What's that distance called? The radius of the Earth, isn't it? Right? And that's a fixed value. You can just look that up on Wikipedia. So here's R. You just plug in the radius of the Earth. And I'll give you that number later too. Right? You guys got all that? Right? And you plug it all in and you get your weight. Right? Now, if you drop that in, then you could solve for the gravity. Actually, let's do that right now. Let's do that right now. I'm going to flip my screen back over here. Let's bump this. Okay, so now we're back over here. I'm gonna do some calculations with you guys. We're gonna do a calculation right here. Let's do gravity field. So I know force equals G m over r squared. I'll use a fixed r, like radius of a planet. Okay? Let's go gravity field of a planet. Okay. See if you guys followed what I just said. Guys, write that formula before I write it. I want to see if you guys follow what I just said. Because you know gravity force, it's gmm over r squared. Right? So what is gravity field? Like the strength of Earth's gravity field. You drop something and it's in free fall. It's falling off the balcony out there. Right? It's accelerating down. Guys, remember it's like this. Right? So just take universal gravity constant, multiply by the mass of the planet you're on, divide by the radius of the planet squared, right? And that's an acceleration value. That's the gravity field, right? And that's true for all objects at the surface. It doesn't matter if you have something small, something big, right? Yeah, if you have 100 grams or 100 kilograms, if you drop those both off the balcony, they accelerate the same. Give you guys some numbers. So universal gravity constant, you guys know, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And you guys told me yesterday it's an extremely small number. Isn't that actually like 0. Let's see if I get this right. 0.0000000000667 Newton meters squared per kilogram squared. Right, I'll give you guys the mass of Earth is 5.98 times 10 to the 24 kilograms. So that's an extremely large number. That's 598 followed by 22 zeros, kilograms. And I'll give you guys also the radius of the Earth is 6.38 times 10 to the 6 meters, right? So think like 6 million meters. 6 million meters. Okay. You guys notice we're using scientific notation because we have crazy small and also crazy big numbers. So we're talking about universal gravitation. Okay, go ahead right now. So gravity field of the Earth equals, set up a fraction. Go ahead and write that in. Write the numbers in where you think they go. And then I'm going to have you guys pull up a calculator that's on your desk and also punch in the numbers on a calculator. I'll do it too, but I want to give you guys a head start. All right, see if you guys are getting this right. Oops. 10 to the 6. All right. So all you guys are doing is you're following, of course, this expression right here. So capital G, I got 6.67 times 10 to the negative 11. I'm going to drop my unit and just pull it outside. Right? I've got mass of the Earth is 5.98 times 10 to the power of 24. That's in kilograms. Okay. And then I've got the radius of the Earth is 6.38 times 10 to the 6. That's meters. And put that all in parentheses, and I need to square that. Don't forget that. Okay. And guys, this all has units. If I pull all my units out, what units have to come out? How do you describe a gravity field? What unit? If you drop something off a balcony, it accelerates at meters per second squared. Right? Or you could also say Newton per kilogram. Here, Newton per kilogram is meters per second squared. So sometimes you see that, but meters per second squared we tend to use. All right, like all the kilograms end up canceling, right? So you get meters per second squared. All right, so I'm gonna do this in my calculator. You do it in your calculator because part of this class, can you correctly communicate with the calculator? And that's, sometimes that's the hang up too. So make sure you can do it. I'll do it. All right. Make sure we're all getting the correct number. 6.67. So I did open parentheses, 6.67 times 10 to the power. Now use the negative if you have this model calculator, which you probably do. Right, do this key at the bottom for negative, not the minus sign, but the negative sign underneath the 3. 11. Close parenthesis, open. 5.98 times 10 power 24. Close, divide by, open. 6.38 times 10 to the 6, close, square. Okay. Make sure this is definitely, well, everything you need grouped together, you definitely have grouped together. If you miss some of these parentheses, then you're not going to get the right answer. So make sure you have grouped together what needs to be in parentheses, just like I wrote it. Right. Now, guys, when I hit enter on my calculator, there's only one number that better be popping up on the screen, and it's what? 9.8 meters per second squared. Exactly. Let's see if it is. Moment of truth. 9.799. Yep, there it is. There's 9.8 meters per second squared. Got it. Now, you guys have been using this number all semester, but now we're saying where it comes from. It comes from how big is the Earth? How massive is the Earth? What's the radial size of the Earth? Like the distance to the center. Got that? There you go. All right. You guys got the gravity field of the Earth. All right. You guys got that? All right. I'm going to flip my screen back over. Let me get this right. Go here. I hit the wrong button again. Hold on. We're going to wait. I got a new system. I'm trying to get used to this. Okay. So I think that. Just hold on. That'll go away. Maybe bump this over here. Share. Okay, that's back there. Come on, play my PowerPoint. Okay, we're good. All right, so we got that. Okay, so you guys know if you drop that little m, you get the gravity field, and you guys just ran the numbers and got the correct value for Earth. Right now, what this is leading into, this is a little bit more. I think this is here. Let's stretch your guys' imagination a little bit. This is again mostly for my AP classes, but I think we got an extra minute here. What if you had this planet X that was 3 times the radius, 7 times the mass? Well, it would be the gravity field at the surface. Because we got two competing effects. A more massive planet. Guys, if the planet's more massive, should that make you heavier or lighter? Heavier. But if you're further from the center, should that make you heavier or lighter? Lighter. Do you guys see there's competing effects here? Because both are happening at the same time. It's more massive, but also you're for the radial distance, right? Now, if it was the same density, the overall effect is you get heavier, but this is not the same density. This is a giant puff planet made out of styrofoam. So, hey, look at this. Gravity field on Earth is GM over R squared. You guys just did this one for Earth. And then if you do it for planet X and just plug in the proportions, then overall it comes out to 7 over 3 squared. Oh, okay, so ratio. Okay. It's a little ratio puzzle. All right, so stretch your guys' imaginations a little bit. All right. This one, orbital speed. All right, here's where we're gonna go back over and do some calculations again, sort of. Right. I want to see if you guys can derive this from scratch. I'll walk you guys through the thought process. Okay? We're gonna do orbital speed. So in your next page of notes, right? Orbital speed. Let's think suppose it's like I don't know, a few decades ago, and we're gonna send something into space the first time. Who knows? Guys, there was a time here that who knows the first thing we ever sent into space? When was that? 19 what? A little before that. 57? 1957? Yeah. Did you guys ever hear of Sputnik? You guys ever hear of Sputnik? Right. Yeah. Soviet Union, wasn't it? Right. Here, give you guys a little extra. Guys, imagine this. Imagine it's like 1956. Nobody's ever sent anything into space. People used to consider, here, guys, here's the sun. Here's the Earth over here. E for Earth. Right. People had some good reasons to believe that there might actually be sort of an opposite Earth over here on the same orbital path, and we could just never see this mystery opposite Earth. Right now, there isn't. But before we sent anything in space, we had no idea. Right now, we got a whole space program, and you guys have cell phones with signals bouncing off satellites and all kind of GPS and all kind of fun stuff. Right, but before 1957, none of those technologies were even available. So, how fast? Suppose you're either a Soviet scientist in 1957 trying to figure this out. How fast do we have to send something into space to orbit? Or maybe an American scientist soon after, but oh boy, we better catch up to them because we don't want them to have an advantage. Okay, how fast does that go? So let's get a diagram going. Here's the Earth. Here's the Earth right here. Okay. Now, the moon is orbiting the Earth. Actually, this is what Newton was thinking too. He was thinking, hey, I think the moon would fall into the Earth, except that it's moving so fast to the side. How fast? Newton was thinking about the same thing. Okay? But I'm going to do something a little closer. I'm going to do a satellite in low Earth orbit. You guys ever seen a satellite go across the sky? You see that? Okay, zip across the sky. It's probably in low Earth orbit, right, which is only about 400 kilometers up, which might sound like a big distance, but compared to 6 million kilometers, in the big scheme of things, it's kind of a tiny proportion. So I'm drawing it that way. Actually, right where I'm drawing the satellite, this orbital path I'm dashing off right here, that's pretty close to scale what it's actually doing. Is that you guys ever heard if the Earth was the size of a basketball and you wrap it in plastic wrap, that plastic wrap could represent the thickness of the atmosphere? Because it's pretty close to what it is, right? All right, so why am I mentioning this? Because here's why. Here's what I'm trying to get at. The radius of the Earth, here's the radius of the Earth right here, I'll just call it R, right, is not that significantly different from low Earth orbit radial size. Right? So they're almost the same thing. Not 100% exactly, but they're pretty close enough. Right? All you have to do is get the satellite above the atmosphere and get it going fast enough. Call it speed v. Right? I'll call the mass of the Earth capital M. I'll call the mass of the satellite lowercase m. Right? You guys got all that? Okay. All right. Okay. So you guys know what we're working toward. We're trying to figure out ultimately what speed does that satellite have to go to stay in orbit. Okay. Let's do a free body diagram on the satellite. You guys ready to do a free body diagram? Is what's one force that's acting on the satellite? Weight. Yeah, the Earth is pulling on it. Now I'm going to label the weight. So put a vector arrow directly towards the center of the Earth. I'm going to label this F sub g for gravitational force. Most of the time I do m times g, right? But I want to be careful with that. Here's why. Do you guys think that the further away you get from the Earth, the gravity field is getting weaker and weaker, right? Right. So, like, especially for the moon, I don't want to do m times g. So I'll just do generically force due to gravity, right? Is the Earth also being pulled towards the satellite? But which force is bigger? The Earth pulling the satellite or the satellite pulling the Earth? They're the same. Yeah, it's Newton's third law. Now, I'm not going to draw the other force though, but because I'm just focused on the satellite. But true. Don't forget the satellite's also pulling the Earth. That's also true. Okay. Equal and opposite force. Okay. Are there any other forces on that satellite? Nope. No other forces. That's the only force. And if that's the only force, that would also make it the net force, wouldn't it? And if that net force, that one force is the net force, is keeping it on a curved path, that means it's also acting as the what force? Centripetal. Ah, guys, here's what you guys just said. You guys just said centripetal force is being provided by the gravitational force. Go ahead and write that in your notes. All right. That's about to be the first domino that's going to kick off a chain that's going to lead us to be able to answer this question. Okay? This does make sense so far, right? All right, you guys got any questions? All right, so centripetal force keeping it in a circular path is being provided by only the gravitational force. Okay? Hang on a minute. I think you guys know some expressions for each of these. What's an expression for centripetal force? It was the answer to your last lab. What? V squared over R? Or you're right. There's an alternate version that goes m omega squared times R. Now that's more useful for like rigid turning disks. Right. I'm looking at a single point mass. Also, when I'm saying orbital speed, I'm looking for like a tangential speed, like the one V that I labeled. That's actually why I'm using this form of it, right? Rather than m omega squared times R. Let's do mv squared divided by R. Right. Okay, so that's centripetal force. That was the answer to your last lab. Because we're in the Play-Doh canisters and the whole deal. That's what you guys got, right? And hey, how about universal gravity force? Now, this one you guys just learned yesterday and today. It's a fraction. What should I put in this fraction? Universal gravity force. How does that go? G M over R squared. There you go. GMM over R squared. Right? You know what? After so many years, I'm still in this habit of like switching my R's, if they're capital or lowercase. I try to use lowercase for a variable and capital for a fix. Right. Let's do this. We're going to do an approximation. You guys remember I made this whole deal about orbital location is not that different from the actual radius of the planet and the big scheme of things. We're going to approximate a little bit. So I'm going to change this lowercase r to a capital fixed R, and we're just going to play off that. Okay, you guys got that? We do that sometimes in physics. Okay, approximate things a little bit. Okay. Okay, so now we got this set up. We've plugged in these expressions and got this equation. Is what are we actually solving for? Which variable are we solving for here? Huh? V. Ah. Right. I want this tangential velocity, the speed. That's what orbital speed is. It's like this V. Right. Okay, guys, go ahead. Do the algebra. Solve for V. I'll give you guys a head start. Okay. So, okay. I mean, I could write it too. I mean, you could copy it. Like, oh yeah, of course that makes sense. But let's see if you guys can get it from scratch. All right, go ahead. Solve for that V right there. A little algebra. All right, guys, figure it out. All right, let's see. Ooh, there's one variable completely cancels. Which variable completely goes away? The mass of the satellite. Hold on to that thought. This might come back to that. And the R partially cancels, not completely, but a little bit. Okay. Oh, actually, you know what? I'm one step away from getting the answer. V equals, how do you undo a square? Square root. That's it. Square root G M over R. That's it. And I'll throw a little subscript orbital on the V. So it's orbital speed right there. Okay. Right. Now this is for a circular orbit. So you want to send a satellite in circular orbit around the Earth? Send it that fast right there. Well, no, this is in terms of variables. Right. Actually, in terms of variables, let's think. I'll give you guys some numbers here in a minute. Have you guys do this calculation? But if you know the mass of the planet, race of the planet, and universal gravity constant, you can figure out how fast to send it. Okay? I forget if I asked you guys this yesterday, but I'll ask it right now. Suppose you got the International Space Station. It's going around. It's got a couple astronauts in it, but they're getting pretty low on supplies, right? And they're getting hungry. So we're going to bring them some space groceries. So we ship them new space supplies. And now it's a lot more massive. Guys, it's so much more massive because they just imported a bunch of supplies. Uh-oh. Is it going to fall out of the sky? Should they have this satellite be going faster, slower, or the same speed to keep it in orbit? Same speed, right? Yeah, great. Yeah, and you guys know that because it cancels out right here. Doesn't matter how massive. Send an astronaut on a space block. You can be maybe tethered to the ship that kind of float outside. They'll go on the same speed. Big heavy ship, little tiny astronaut. Yeah, it's all same speed, the same speed. Okay, M cancels out. Little m. Okay. How about this? Okay, suppose you send a space probe to another planet and you send it in orbit and you kind of do trial and error until you get it in orbit and say, okay, now we figure out how fast it's going. We see its orbital radius because we just kind of look at it and see that. We know what capital G is because Von Jolly figured that out in 1880. Okay. Do you think you could, in principle, back calculate what is the mass of the planet that's being orbited? Yeah, you could do that too, right? If you know any number of these variables, you could solve for the one unknown. Okay. We're going to solve for orbital speed around the Earth. You guys ready to do that? Orbital speed around the Earth? Right. Now you guys have some Earth values right here. So let's take these Earth values. Now open up a new, I got this paper right here. Remember this paper right here. Right. So here's universal gravity constant. Here's mass of the Earth, radius of the Earth. Let me make sure it's showing up on my Zoom. Yeah, okay, got that. Okay. And you also know orbital speed. You have an expression for it now, and it goes square root gm on r. So let's do this for the Earth. Let's do v orbital for the Earth. Right. Say equals. I got a big old square root. There's a fraction in here. And part of the trick is, can you plug this correctly into your calculator? So that'll be a challenge too. Okay. All right, where the G goes, let's put 6.67 times 10 to the negative 11. I'll bring my units outside after the fact. It's a little prettier. The mass of the Earth is 5.98 times 10 to the 24. That's in kilograms, but save my unit for later again. Okay. The radial size of the Earth down here, 6.38 times 10 to the 6. That's how many meters? I think 6 million meters. Make sure that's definitely all grouped in parentheses, especially when you plug that in the calculator. See, I put some parentheses there. Make sure that's in your calculator. Now, this is all underneath the radical, so I'll throw in some extra parentheses right there, right? And then, oh, I need some units. I'll pull all my units out. Because when I pull all my units out, what units is this naturally going to come out to? Meters per second, because it's an orbital speed. Tangential speed. Okay. All right, calculator time. Guys ready to try this out? Pick a calculator. So second square root, so get a square root. Now, if you have the same model calculator that I do, then when you hit square root, it opens up one parenthesis, but be careful, because as soon as you close the parenthesis, it stops square rooting. But I see a bunch of stuff underneath that radical. Here's what I'm going to do. I'm going to open up additional parentheses. You see I just opened up additional parentheses? Right. Now, this model calculator automatically closes. So if I have excess parentheses, it'll automatically close them. Not all calculators do that, so just watch for that. Right. But I don't want too few parentheses. So I've got definitely plenty of parentheses here. You guys see that? Okay. So let's do 6.67 times 10 to the negative 11, close open, 5.98 times 10 to the 24, close divide by open, 6.38 times 10 to the 6. Right. Okay. And then again, this model will naturally close my excess parentheses. I lose count. Okay. Right. Now, when I hit enter, it should tell me the correct orbital speed. That maybe the Soviet scientists and American scientists were trying to figure out back in the 1950s. Okay. All right. You guys plug that in your calculator. Okay. What number did you guys get? Huh? Did you say 7,900 or something? Yeah, sounds like you did it right. Aha. Let's see if I did it right. Okay, yeah, I did it right too. Right, because all right. So V orbital for the Earth equals 7,907 meters per second. Now this is for a circular orbit for low Earth orbit. Okay, so if you're say just above the atmosphere, and you're going in a pretty circular orbit, you want to target the speed right here. Okay. Good. Suppose you went a little bit faster. Because what if you're going 9,000 meters? Because sometimes I'll round this to 8,000 meters per second. Okay. Right. Because 8,000 meters per second might be a circular orbit around the Earth. Here's the Earth. There's a circular orbit. Okay. What if I was going 9,000 meters per second? What would the orbit look like? You think it would elongate into maybe a ellipse? What if I go 10,000 meters per second? You think it's going to be a longer ellipse? And then 11,000 meters per second. Because what if I hit 12,000 meters per second? Guess what happens at 12,000 meters per second? Rocket's going to fly away. It's something called escape speed. Escape speed is equal to, here, I'll tell you for Earth. It's the square root of 2 times this, which comes out to about 11,200 or so meters per second. If you get a rocket going that fast and you cut off the engines, it's going plenty fast enough. It's going to fly away from Earth's gravitational field and fly off into space. Okay. And that's I think a slide I have coming up. So let me flip back over to this. All right, here we go. That's orbital speed, right? Right. Now, escape speed involves conservation of energy, which we haven't even talked about in this class. There's different ways you can teach this class and different orders of things, but I want you guys to see the end result here. You guys see escape speed and see that expression with the square root? If I toggle back and forth, you guys see orbital speed and escape speed look really similar? If you know orbital speed, all you have to do is multiply by the square root of 2 to get how fast you have to go to escape. That's it. Right. And then, here they are very conveniently all on one slide. Right, so we got gravity field of a planet, gm on r squared. Here's the orbital speed, which you guys just derived in your notes. I had you guys figure that out. And here's escape speed, which is actually a future topic. Okay. All right. I have a few more gravity slides that are pretty fun, but this is about where the bell's been ringing. So we are going to hang this up for today. Call this a wrap.